Okay, let's unpack this. Today, we're taking a deep dive into, well, the really fascinating world of sound and waves. Specifically, how seemingly complex signals are actually built from surprisingly simple components. Our source for this is a look into the interface of something called a Fourier Series Explorer. It gives us a high-fidelity Fourier simulation. So our mission really is to understand how this explorer visualizes the decomposition of sounds, showing everything from just a basic single 1 Hz wave up to fundamental shapes like square, sawtooth, and triangle waveforms.
Yeah, and what's really great is that the tool doesn't just stop there with the basics. It also brilliantly demonstrates how you create more elaborate things like a complex tone or even a 3-tone chord. And it shows that interesting phenomenon of beats, too. It even gives a specific example like combining 2 Hz plus 3 Hz. Plus, we'll look at some other intriguing bits like center of mass and controls. You see like 0, 0, 0, 0, 0 cycle-second audio, off, and drawing speed. These all offer some, unique ways to understand and even manipulate these basic building blocks of signals.
That sounds like a fantastic roadmap. Okay, so let's start with the absolute fundamentals then. This explorer kicks off by showing us that single 1 Hz wave. What's that basic wave telling us? Why is it so crucial?
Well, what's fascinating is that single 1 Hz wave is just the most basic sine wave you can have. Smooth, repeating oscillation. It's really the simplest ingredient, in the whole recipe of sound. The core idea behind Fourier series, and what this explorer shows so clearly, is that any complex sound wave, doesn't matter how intricate, it can be broken down into a sum of these simple sine waves, each with its own frequency, its own amplitude. It's kind of like taking apart a complex dish back into its individual spices.
Right, I see. So if that's our basic building block, how does the explorer then show us something like a square wave or a sawtooth or triangle? Yeah. What makes those fundamental, and what do they actually sound like?
Good question. So these waveforms, square, sawtooth, triangle, they're fundamental because they have these distinct, recognizable harmonic structures, meaning they're made up of very specific sets of those sine waves we just talked about. Okay. A square wave, for instance, it sounds kind of buzzy, a bit hollow. That's because it's built from an infinite series of odd-numbered harmonics. The explorer actually visualizes adding these odd sine waves one after another. You see how their sum gradually makes that sharp square shape? A sawtooth wave, though, sounds brighter, fuller. Think like a brass instrument. That's because it contains all the integer harmonics. And the triangle wave, that one's softer, maybe more flute-like. It uses only odd harmonics, too, but their amplitudes drop off faster. The simulation lets you literally see these simple signs stacking up. It's pretty cool how they create these complex, distinct shapes and sounds.
Yeah, it really is incredible to visualize that. Okay, so once we get how those fundamental shapes are built, how does the explorer move on to showing more elaborate things, like a complex tone or that 3-tone chord?
Right, so this is where we shift from taking things apart to putting them together. Deconstruction to construction. The explorer takes those individual sine wave components and shows how, by combining them in specific ways, you can build something much richer. A complex tone is essentially just a sound made of multiple sine waves that are harmonically related, meaning they're integer multiples of a base frequency. That gives it a richer timbre than just a plain sine wave. A 3-tone chord then just takes it a step further. It combines 3 distinct frequencies, often chosen to sound, harmonious or maybe dissonant. And the visualization really shows how these individual waves interact, reinforcing here, canceling out there to make the overall shape of the chord.
And what about beats? The source mentioned 2 Hz plus 3 Hz. That sounds simple, but what's happening? What do beats sound like?
Beats are a really interesting auditory effect. They happen when you play 2 sound waves with just slightly different frequencies together, like with 2 Hz plus 3 Hz. You don't really hear 2 separate tones. You hear a single combined tone, but its loudness, its amplitude goes up and down rhythmically. The explorer shows this really well. You see the 2 separate waves, then you see their sum, and you'll notice the resulting wave's amplitude getting louder and softer periodically. That's the 2 waves interfering, constructively and destructively. It creates that distinct wah-wah-wah, or like a throbbing sound. It's actually used a lot when tuning instruments.
That makes sense. It's a perfect example of simple things combining for surprising effects. Now, beyond just showing the waves, this explorer has some interesting interactive bits, like center of mass. What does that tell us about a signal?
Yeah, the center of mass here is a really clever visual cue. In signal analysis, it sort of helps us understand where the sound's energy is concentrated, or you could think of it as its auditory weight across the different frequencies. If the center of mass is lower, it suggests more energy down low in the bass frequency, so heavier sound. If it's higher, more energy's up high. A brighter sound, maybe thinner. It's a quick way to just gauge the overall tonal balance of a complex wave.
And those other controls, like 0.00 cycle second, audio, over, drawing speed, how do they help?
Right. Those controls are actually pretty powerful for digging deeper. Setting 0.000 cycle second, that basically freezes the animation, stops the waves moving. So you can really inspect the waveform at one point in time, see its exact shape, how the components line up without the motion distracting you. Audio Auto-F is simple but useful. It lets you just focus purely on the visuals first, which is great for learning. Then turn the sound back on to connect the two.
Yeah.
And drawing speed, that's fantastic. You can slow the whole process right down, see each sine wave component being added step by step, building the complex wave. It really makes that abstract idea of summation feel, well, tangible.
So what does this all really mean for us? I mean, this deep dive into the Fourier Series Explorer has really shown quite vividly how the fabric of complex sounds, from a three-tone chord to those intricate beats from 2 hertz plus 3 hertz. It's all elegantly built from basic elements. Things like square or triangle waves, and it's all visualized through this high-fidelity Fourier simulation. It's like seeing the simple parts inside the complex whole.
Exactly. And, this raises kind of an important question, I think. Considering how a simulation like this can make the invisible world of frequency and waves so tangible, so understandable, how might understanding these fundamental principles like Fourier analysis, like center of mass in signals, how might that empower us? Could we use similar ideas, this deconstruction approach, to understand other complex systems in our world way beyond just sound? How can breaking something down into its core components help us understand, well, almost anything better?
That's a really powerful thought to end on. Thank you for joining us on this deep dive.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.